Hello, my name is Younghun, and I'm going to present about aggregating funnels, which is a joint work by myself, Yuanhao, Eric Ruppert, and Panagiota Fatourou, Siddhartha Jayanti, and Julian Shun. So what is Fetch&Add? So Fetch&Add is a fundamental atomic instruction which is widely used in many distributed and parallel programs. And basically what it does is to fetch the value of the variable into the variable and also increment or add certain value to that variable atomically. So as you can see in the pseudocode in bottom right, this whole process should be happen atomically, so no other process or threads can see the intermediate values while the other thread is working on the fetch&add. And this fetch&add operation is widely used, and it's often is a bottleneck in higher performance programs. For example, this fetch&add is often used in assigning timestamp to database transactions or maybe network packets in load balancing systems, or also it's also used in various high-performing data structures such as concurrent queues or ticket logs. Also, it can be used in reference counting, garbage collection, and so on. Because this fetch&add is so universally used, basically all modern CPUs support the hardware instruction support to do this fetch&add operation. And if you want to use the fetch&add in your program, then you might want to look through the standard library of your language. But the problem here is that um, we don't need to know about the details of the hardware implementation, but basically, if multiple threads call the hardware fetch&add instruction in one variable, then they all have to wait to each other to finish their fetch&add. That's basically they all sequentialize on this main variable. For example, if there were two threads trying to do fetch&add in variable X, then let's say red thread goes first, do the fetch&add in X, and while red is doing this, blue thread has to wait until the other red thread finishes its work. And then only after red thread finishes, then blue thread can go on and access the main variable. Because of this sequentialization, you're not going to get additional parallel speed up even if you throw multiple like 100 or 1,000 thread after you reach the bottleneck of this sequential fetch&add performance throughput. So the overall main topic of this project is how to find a way to mitigate contention in efficient way. And our contribution is first, we offer or provide a scalable novel fetch&add algorithm which efficiently mitigate the contention. And in our micro benchmark, we saw that throughput was faster than hardware fetch&add up to 4 times. And also to show that this algorithm, our new algorithm, is actually usable and can be used in practical real-world problems, we plug this fetch&add implementation into state-of-the-art concurrent queue and compare the results, compare the throughput between our version of LCRQ and the other existing version, previous work. And we saw the throughput was faster than the previous version, more than 2.5 times. So, way to mitigate contention, there are certain ways, certain approaches we can take in previous work, and we're most tried ways to mitigate contention is software combining. So basically, software combining algorithms combine multiple operations from concurrent threads so that some thread will be the delegate and still go to access the main variable, but some other threads will be the waiting thread and will wait until that delegate thread do its work and get the values back. So for example, in this diagram, you can see 3 threads trying to do fetch&add in main. And let's say the order can be arbitrary. Let's say red thread goes first, and they all climb through the binary trees to access the main. And while they are climbing, they might see each other like this. And if they see each other and they decide to form a batch, then one thread will become a waiting thread and delegate their work to the other one. So in this case, red thread will be the waiting thread and give the delegate their work to the delegate thread, which is a blue thread. So blue thread will carry two operations from now on, and then try to do both, apply both at once to the main variable if it reached the main variable. As the time goes by, the green thread comes along and also climb up the tree. Order can be arbitrary, and also blue thread can see green thread here, and then it can also delegate two red operation and blue operation to the green thread, so that green thread carries three operations, and it will apply to the main variable at once, all the time, all at the same time. So green thread will do fetch and add in main variable and get the result of 0 as a return value. But since waiting thread didn't reach the main variable, they don't know about their corresponding return value. So the delegate thread or green thread has to propagate the corresponding correct return value, the state of the main variable, to those waiting threads so that they can return their corresponding correct return value. But this is how the previous algorithm works basically. And those algorithm has some notable problems, which is they require multiple atomic operations per combining, which means per combining, it's very high overhead. And also the previous work only supports two-way combining instead of k-way or more than two threads combining at once. So because of this, combining is slow, and also combining happens infrequently. Therefore, those algorithms have to use deep enough trees so that they can reduce the contention enough because the combining rate is so low. And our approach is to design an efficient k-way combining algorithm, which means we can support k concurrent threads, k concurrent operations combining at once and to form a one batch, therefore reducing the contention much more efficiently. And also for each batch, we only need one additional fetch and add per combining. Therefore, the overhead in our algorithm is much significantly lower. While designing this efficient k-way combining software combining algorithm, there are certain challenges to keep in mind. For example, we have to decide how to define the batch and when or where the threads see each other and form a batch. And also, when the batch is formed, you have to figure out a way to choose the one delegate among those k threads, because in this algorithm there can be multiple threads, many other threads trying to be a delegate. And also, after the delegate is chosen and delegate does the work to the main variable, we have to the delegate thread has to propagate the return value to many k-1 threads. So that propagation process has to be also very efficient. Furthermore, we would like to increase the combining rate as high as possible so that we can achieve low contention with only with low overhead as possible. So let's go see the details and see how we achieve this. In this presentation, we will consider only the positive fetch and adds, although our full algorithm supports both positive and negative fetch and adds. So in this example, the main value will always increase as the operations are applied. In our algorithm, we keep one significant data structure which we call aggregator. So in aggregator, threads will be assigned, and also those assigned threads will start from their corresponding aggregator to form a batch, and some delegate thread will go to the main if they are chosen to be. And also aggregator keeps two internal fields, first one is the internal value, which is an integer value you can see in the diagram inside the aggregator. And the other one is linked list of batch history, as we can see in this batch. So for the first batch, let's say red thread came along and tried to do fetch and add in main. And because there are no concurrent threads, red thread becomes a delegate itself, and it just applies the fetch and add 8 to internal value and main variable. So In this diagram, in the square there, we represent the batch history entry, single entry. And we keep three numbers in the batch history, which is an aggregator start value and the end value. So if you see the history, you can see the red thread increased the aggregator's internal value from 0 to 8. So we're going to keep that history inside this batch to show that this internal value has incremented from here to here as an interval. And also we're going to keep the other value, which is a main start value, which means the interval of this batch will occupy the interval starting from this 10 of the main variable. So conceptually, the interval size of 8 will occupy the main variable from 10 to 18 because red thread has incremented from 10 to 18. And this goes on with the green thread. Let's say green thread came along from the different aggregator, and its batch history will be kept in the other linked list in that aggregator. As you can see, the green thread incremented the internal value from 0 to 5, and also the state of the main variable was 18 at the time the green thread reaches the main variable. So we're going to keep that three numbers in this batch history, and also conceptually, as bottom diagram shows, this batch will occupy from 18 to 23 as its return value. Let's say the case of combining happens. So let's say blue and yellow thread both starts from the bottom aggregator and happen to be combined, and blue thread happen to be the delegate thread. And in that case, blue thread will apply both of the operations to the main variable, although blue and yellow thread will respectively do the fetch and add in the internal value of its aggregator. You will see this in the following example of the sequence. And in this blue batch, the internal value of the aggregator is still increased from 8 to 20, and though that interval will be saved in this batch, and also this interval will occupy the main interval of starting from 23, reaching to 35. So the algorithm, the pseudocode is like that, and we're going to see the same execution of the blue and yellow thread concurrently. So in this state, as we saw in the previous slide, the aggregator has the internal value of 8 and main variable is 23. And we have one batch history from the previous batch, which is the red threads batch. And let's say blue thread come along first and try to do the fetch and add in aggregator's value. So it will do the fetch and add 10 to this aggregator internal value and increment from 8 to 18, 10 to 18, sorry. 8 to 18, sorry. So at that time, blue thread will keep the state of the previous internal value to its memory, and we call this as a ticket number. So blue thread has ticket number of 8, and let's say, oh, by the way, the blue thread will wait on this batch history until the last batch is done just before its operation. So let's say because blue thread have ticket number of 8 and also batch history has just ended, shows that the previous batch has just ended by the 8. Now blue thread knows that it is the first thread to come to do this fetch and add, so it knows that it can be the delegate by itself. After that, let's say yellow thread comes along and try to do fetch and add in the main internal variable and do fetch and add from 18 to 20. And you will get the fetch ticket number of 18 and try to spin on the list until all the previous operations are done before it itself. In this case, yellow thread has ticket number of 18, and the batch history still says the operation was ended at 8. So yellow thread doesn't know whether it should wait or become the delegate, and it will wait until there's an update on this batch history. From here, blue thread as a delegate thread will go on and try to read the aggregator's current value, which is 20, and get the 20 and get the difference of 20 and its keycap value, which is 8. So there's a difference of 12, which the blue thread will apply 12 fetch and add to the main variable, and it will increment from 23 to 35. And at that point, blue thread will know the previous state was 23 and think that it knows that it will be its return value. And after doing fetch and add, blue thread will come back to the batch history and update the list to let the other waiting thread, if any, and let the other thread knows that the previous operations are done to this extent. So there will be an update to the linked list of batch history, which says that for internal value 8 to 12, 20, this interval is all done. So at this point, yellow thread can know that its operation is actually done because 18 was its ticket number and the current state of the aggregator is already past 18. So it knows that its operation is already done by someone else and try to reconstruct its return value based on that batch history. Because it knows the ticket value and because it knows where that interval starts, where that interval occupied in the main variable, it can reconstruct by offset, and it will return 33 as its return value, as if it did fetch and add in the main variable. So that was the detail of the algorithm, and let's zoom out and let's see what we actually achieve. So basically, essentially, we just distributed contention from one variable across m+1 variable. Let's say m is the number of aggregators, and we across those contention to those aggregators so that we can achieve the lower contention of max of m comma p over n, which can be minimized when number of aggregator is actually square root of p. But the trade-off here is that because to reduce the contention of the main variable, we added one more fetch and add for some delegate threads, for exactly delegate threads. So delegate thread will do fetch and add twice, once in its aggregator and once to the main variable, but the waiting thread will only do the fetch and add in its aggregator. But because this overhead, this trade-off is not too much, and the contention was the bottleneck here, we could achieve the higher throughput overall. In our experiment, we tested with the 4-socket with the two-way hyperthreading, which has about 196 threads. And in this experiment, we tried to find a good aggregator count in our algorithm and workflow. We tried with multiple constant number of m, and as well, we also tried with the square root of p aggregators to see whether the theoretical minimum of the contention is actually optimal in the practical sense. But in this experiment, we saw when we have 6 aggregators, it was performing overall the best, and we're going to use that version, that number m equals 6 in the subsequent experiments. And it's worth noting there are some significant previous projects on this. So first try to mitigate contention was to try to implement this distribution of contention by hardware switches, which is stated in the NYU Ultra computer. And there are multiple scheme of software combining, which we saw the combining funnels was the most advanced and most performing one, and we combined with those. In conceptual sense, in comparison of algorithm, we saw some notable differences between the two combining funnels and our aggregating funnels. As noted, our aggregating funnels support the KY combining with only single fetch and add, but combining funnel, it only supports the two-way combining with multiple use of caches. And also we only need the depth equals 1, just shallow combining tree as instead of log p depth of combining tree because of the low combining rate. Also, the propagation of the return value from delegate thread is also much more efficient in our algorithm because the delegate thread only posts the return value in the batch linked list of batch history, and all the waiting threads will reconstruct by itself reading from those information by parallel. But on the other hand, combining funnels delegate pushes return value to sequentially to the waiting threads, so propagation is also much slower in the combining funnels. And we also could saw that in the we also can see that in the experiment values, experiment results. As you can see, the hardware is on the bottom, and combining funnels as a purple line is around the same throughput with hardware in the highest number of threads, but our aggregating funnels was much more performant in highest thread and far more scalable. And we plot our before that, we have to state about the current status of the concurrent queue. So it is known for about a decade that LCRQ was the most performing version of the concurrent queue, and the state-of-the-art queue, LCRQ, actually uses linked list of ring buffers. So it basically keeps two integer variable to keep the index of tail and head, and it goes on which fetch by doing fetch and add in each variable. So it is known that this contention was the bottleneck of this performance of LCRQ, and we just put our implementation of fetch and add inside the known implementation of LCRQ, and we saw the performance was faster by about 2.5 times compared to the hardware fetch and add. So to conclude, our project provides the new aggregating funnel algorithm for fetch and add, which is much more faster than the hardware fetch and add. And also in paper, we prove that our algorithm is strongly linearizable and also can be used in joint of other read, modify, write atomic operations. And also it is much more fairer in the sense that most threads get the even number of the operations done. And also by using this algorithm in the LCRQ, we provide the faster than the state-of-the-art concurrent queue, and it is actually the practical drop-in replacement of the hardware fetch and add, even in the other applications as well. Also, we publish our codes and hardware artifact in this GitHub, so it can be used as future work. For future directions, we can think of many different significant ways, interesting ways of doing this. For example, we can implement this in hardware, for example, in CPU, specific types of CPU or even GPUs, to make sure that this the fetch and add operation can be much more faster in the hardware level as well. And also, we fixed the environment and the workflow of this in our micro benchmark. So it should be explored that whether this algorithm can be adaptive and used in dynamic configuration by itself without any pre-tuning process per workflow or environment. And also, we may think of the better way to formulate the contention model, because contention model is a bottleneck in many different applications, but there are not enough research in giving theoretical insights on this models. And also this general idea of software combining can be used in different applications, for example, generalized operations or maybe specific use cases. And also that we can try to explore whether this algorithm scheme is performant in many different or more application level complex system. Thank you.